your rolling process. So probably rolling process was not discussed in detail. We have, I think, done some numericals from this process, from this kind of forming process, but we haven't discussed the theory behind this process and the way how the forces and the pressures can be derived. Okay. So if we will quickly go through the basics of rolling process and the derivation of the pressure, roll pressure, and then I hope that will make your concept a little clear about this rolling process. So starting off, rolling, is one of the most important kind of forming processes because mainly of the cost effectiveness, uh, high productivity rates, high production rates. So generally rolling is what? Rolling is a kind of process in which sheet metals, okay, are rolled with two rollers rotating in opposite directions, right? So that way you can reduce the thickness of the sheets through the rolling process, but the width in that case of the sheet that is considered to remain constant in the rolling process. Okay? So by width, I mean this width of the sheets, okay? W actually remains constant. If you take W1 initially, and W2 finally, then W1 happens to be equal to W2 in case of rolling process. Okay. So in that case, just like any other metal forming processes, rolling works in the same way. The deformation takes place when a compressive force is applied by this oppositely rotating set of rolls. Okay. So this deformation actually reduces the cross-sectional area of the metal and converts it into a record shape. However, you should note that unlike any other forming process, rolling process is a volume constant process. The term is volume constancy, which is used in that case. So the initial volume is happens to be equal to your final volume. Okay. Now, the main purpose of rolling is actually to reduce the thickness of the metal sheet, okay, just like the billiards, blooms, slabs, plates, etc. And probably steel, aluminum, magnesium, copper, and of course their alloys are the materials which are commonly rolled. Okay. So as you pass plate between the rolls, the friction of the friction at the interface between the plate and rolls actually converts into heat, and that way the rolling process gets over. Okay. Now, why is it such widely used is the mainly related to its production rate. We have a high production rate of rolling processes. Okay, then the grain structures, you can actually obtain your desired grain structure, which can be of good strength, which can offer you good strength and longevity. Okay. And also ductility, and then as per your requirement, as per the requirement of the end process. Okay. Now, continuing ahead, we look to two types of commonly known rolling processes, which are hot rolling and cold rolling process. Okay. So in hot rolling process, actually the metal is fed between the rolls when it has already been heated above the recrystallization temperature. If you are not acquainted with recrystallization temperature, it is actually the temperature after which there is an internal change of the grains. Okay? There is new crystal formation out of the old ones, and so when this temperature is already crossed, then the material is spread into the rolls. Okay? And in case of cold rolling process, it happens that material is spread even before the recrystallization temperature is reached. Okay? So that is the major difference in case of hot and cold rolling process. And so very thin sections and sheets can be obtained through hot rolling because the material is already soft. And in case of cold rolling process, up to 0.02 mm or 20 microns, you can go. Okay. Now, of course, because high heat is required in this case, so the microstructures happen to reform and recrystallize, and you may need high post-processing in case of hot rolling processes. But because the metal is already soft, you need very less time to process, and the time taken is very less, okay, and also cheaper in case of hot rolling process. So these are the advantages of hot rolling. However, there can be issues with the microstructures and the final property and density of the product you are obtaining. So that is the thing about hot and cold rolling process. You can look at the diagram on the right hand side. Here you can see the grains heavily distorting and recrystallizing into smaller ones because of the high heat and compressive force acting between the rolls. And in case of cold rolling, you can see these are rather columnar in appearance. Okay? So that may actually cause high differences in the properties of the initial and final product which we get out of the rolling process in case of hot rolling. Okay? Whereas in cold rolling, you can simply get out your less distorted or much of the properties remains constant or undisturbed, okay, after your cold rolling process. So processing ahead, let's go to the mechanics of rolling process, but this we need some initial concepts for you, which are draft and spread. Okay, so draft is actually the differences with the initial and final height of the sheet which has been rolled. And spread is the difference between the initial and final width of the sheet, which actually I mentioned before remains zero in case of rolling process. Now, you may be asked a question that suppose you don't use any front and back tensions, that is the unaided entry, means you don't give any tensions at the start and behind, okay, and back of the process. So for that case, what should be the condition? Okay. Now, if you just look at the normal force acting on the strip, okay, during the rolling process at the interface of the roll and the sheet, P, you just bifurcate this into the components P sin alpha and P cos alpha. Okay. And then you also take down the friction force mu P at the interface, and then you bifurcate this also into sin and cos components, and then just equate the both in the horizontal direction. Okay. So in one side you see that you have mu P cos alpha, and on the other side you see you have P sin alpha. Okay, just the sheet will stick to the roll only when the force on the left hand side happens to be greater than equal to that on the right hand side, right? So otherwise the roll will shift away from the strip or the sheet which is being considered for rolling. So in that case, mu p cos alpha should be greater than your p sin alpha. Alpha is the included angle at the interface. Okay. So that case, your mu or friction coefficient. Okay. So mu is your friction coefficient. Should be greater than, you just take the left hand side component p cos alpha to the RHS, and then you get mu happens to be greater than equal to 10 alpha. That is the initial criteria during your rolling process for unaided entry. Okay. So proceeding, there are certain things called the contact length, the maximum reduction purpose, and the bite angle alpha, which is included at the interface of the roll and the sheet. Okay. So by sector formula of a circle, in that case, you can see if you have a bisection line, suppose this y-axis, okay, if this is bisecting the x-axis at this point, okay, so in both sides, suppose your length is L and L, okay, L and L, and then so you have L cross L equal to the two components of your bisected part of the y component. So this part, the whole radius is twice of r. Okay, if r be the radius of the roll, then twice of r minus of this part. Okay, so the total reduction, because of this side also there is a roll, right? So here also you have a reduction of del h by 2. So in that case, the total del h by 2 plus del h by 2 should be your total reduction purpose del h. Okay, so in one half you have del h by 2, and then del h is h1 minus h2. Okay, if you are confusing, then this part is del h by 2, and twice of r, that is the dia of this roll, minus of this part del h by 2. Okay, gives you this particular distance, isn't it? 2 or minus of del h by 2. And this one is only your del h by 2, as you have discussed just now. So by sector formula, you do this L cross L, L be your contact length. We are considering in that case, suppose this is your roll, this is your sheet. Okay, so we are considering that this distance should be equal to this distance. This is your contact part. Okay, so we are just assuming that this distance should be equal to this one. So these are at very minor scales, so not much difference are there. Looking at this particular L value, you can actually get an idea of what is the contact line, right? So you just do L cross L equal to 2r minus del h by 2 multiplied by del h by 2. From that you get the contact length as root over r del h. Okay. R is the radius of your roll, del h is the maximum reduction purpose. Now in that case, you can find a term called del h by 2 squared. So already del h happens to be very small, half of that further small, and the square of that smaller. Okay, so we just ignore the higher order terms and find out that the contact length then becomes the square root of r multiplied by your maximum reduction purpose, this del h. Okay. And now we look at another thing from here, which is called as the bite angle, which is subtended at the roll, okay, at the contact of roll and streak. So from this figure again, you can see that cosine of this angle alpha happens to be r minus your del h by 2. Okay, so this whole thing, so So this whole thing is your radius, right? This is your R. So you just subtract this smaller part, okay, this one from R, R minus del H by 2. Okay? So this small portion, this tiny portion is R minus del H by 2 actually. And then you have the hypotenuse R. So that will give you cosine of your angle alpha. And using that, you just factorize that or divide that single-handedly to get 1 minus del H by twice of radius R. So that is good. That is actually 1 minus your del H by diameter of this roll D. From that, you can get alpha is your cos inverse of 1 minus del H by D. So further take it down, you can also see this is almost equal to tan inverse of root square root of del H by R. Okay, both the same thing. You can calculate it by using both the formulas, and from that you go to finding your maximum reduction purpose. Okay, you just uh, square both sides, okay, and then you can see that tan square of alpha multiplied by radius of roll R gives you the maximum reduction purpose del H. Okay, again, tan alpha is we have just seen in the last slide that tan alpha should be greater than equal to tan alpha, right? So the limiting case is mu equal to tan alpha. Okay? So use that concept here and replace tan alpha by friction coefficient mu, and see that del H equal to mu square R happens to be your maximum reduction purpose, which you can get in your rolling process ideally. Okay? So are these things clear to you all? Okay, so assuming that these small concepts are clear to you all, we'll proceed to our next slide, which actually deals with the mechanics of rolling process. Okay, so as you have seen earlier, suppose this is one roll and this is one roll rotating in opposite direction. You should know that both these rolls should rotate in opposite direction to take the strip forward through them, right? So just in that case, theta is same as alpha, which we used in the last slide, and d theta be your differential angle. Okay, and we take the strip at that particular angle of thickness dx. Okay? So let this be the strip of thickness dx, and then you have a normal force P, just similar to the last one, okay? As we have seen that, right? So here you have seen this normal force P acting at the interface. So it is same as that. We have taken out the strip. The normal force P acts on its surface, and normally to that, now we have the frictional force mu P. Okay. Now let us suppose that in the right side you have a stress component along the x direction sigma x, and there is a differential increment in that component on the left side, which is sigma x plus d sigma x. Okay. The friction force should act similarly in both sides. Okay. Here you should also find out a P force, right? So let's suppose in this y direction, suppose this is up to y, and here you have an additional increment dy. So this whole length here becomes y plus dy. Also, let us consider sigma xi is your back tension and sigma xf is your front tension. Okay. So considering all these things, you just do the equilibrium in that direction, right? So twice, why twice? Because the same forces will be acting in both the sides of the stream. So whatever we do, we take twice of that. So y plus dy, sigma x plus d sigma x. Okay. Force balance, right? So stress into area, we take unit depth of this sheet. So W becomes 1. And then out of the area, we have only y plus dy. So y plus dy into sigma x plus dx on the LHS and y into sigma x in the RHS. Okay, sigma x into y on the RHS minus of twice of RD theta into mu to cos theta. What is that? That is mu to cos theta is your frictional force. Okay, so if you resolve these components, right? So in this direction, we will find mu to cos theta. Okay. And in this direction, okay, you would find T sine theta, right? So when you do that, you just take the equilibrium of these forces. So mu to cos theta and the corresponding area is this strip area, okay? So it is almost equal to RD theta. That is for a segment of a particular circle. Okay? If you look at that circle, it is having a radius R. Okay? At a particular differential angle d theta. So what is the arc length, right? So this is R, and the arc length becomes arc times of d theta. So that is what, and for both sides you have a 2 multiplied, and then this is the force, frictional force, okay, and this is again acting on your left hand side, 50 sine theta. So that's why it is a positive sign. So the whole force balance you equate to 0, and you come down to this particular expression after just resolving, after just taking out. I have excluded some intermediate steps which you can do at home. Okay, so here finally you can get differential of y into sigma x. Okay, you can take the intermediate steps and uh, just exclude the much smaller terms. Okay, suppose there is a term coming out dy d sigma x. Okay, so both of them are very negligible. Okay, and the multiplication of both further reduces it in terms of magnitude. So just ignore this type of terms and take out the other terms, and you finally get differential of 1 into sigma x, okay, minus of radius of the roll r, okay, into p, the pressure, the force, okay, normal force p acting on the strip, multiplied by the difference of the friction coefficient and the angle at the center, your right angle, multiplied by d theta equal to 0. Now we just consider that for small theta, the cos theta becomes 1 and sin theta becomes 0. Okay? So that way your cos theta and sin theta components will go away from this expression, right? So this would become your final expression, and then you just assume, as you have already assumed theta to be much smaller, we can consider sigma 1, your first principal stress, to be equal to the stress in the x direction, which is sigma x. Okay, from strength of materials subject. Okay, you, I think, know about principal stresses and strains by this time. So I'm not going to into the details of the principal stress strains. Okay, that we have actually discussed sometime in the forming, in the session which we covered forming process. Okay, here we just consider sigma 1 to be equal to the stress in expression sigma x, then sigma 3 be equal to minus of sigma p, okay? Because it is acting downwards or it is compressing in nature, we take it as the negative of the component, okay? Minus of p, and then sigma 2 becomes the average of both these forces, okay? Half of sigma x minus p. Now, from forming, you know about the von Mises criteria, which we use to determine a relation between the various stress components, right? So just plug in these particular values in the von Mises criteria equation, where K is a strength coefficient, okay? So you just plug in the values and find a relation between your sigma x K and your normal force, normal composite force P, right? That comes out to be a sigma x equal to 2K minus P. You take that particular value of stress in the x direction and just place it in your equation 1, which you found from force equilibrium, okay? A differential of sigma x into y minus of rp mu minus theta d theta equal to 0. We just plug in the value of sigma x equal to 2k minus p in this case, right? And you find out this particular expression becomes 2ky, which are constants. Okay? You take them outside, right? And then you do the differential of 1 minus p by 2k. How do you do that? So just take 2k, you divide the whole term by 2k. So this becomes 1 minus p by 2k, right? And 2k comes out here. So this becomes 2ky, and then d theta of whatever left, which is 1 minus p by 2k, right? And then you take this minus out, and this term becomes plus, and you reverse it to theta minus of theta plus of mu. Why this is minus plus? So this is something related to the change of the friction coefficient with time. Okay, the frictional force can sometimes become the friction coefficient can sometimes become positive, can sometimes become negative. So to take account into the direction variation of the friction force, we have taken minus plus sign both here. Okay. Multiplied by rp happens to be 0. Now, as theta is small, as we have discussed in the last slide, so y can be represented as pf by 2. Okay, so if you look at the strip here, so here you have pf by 2. If the whole thing and the whole thing with thickness of pf, so half of it becomes pf by 2, right? And this thing again becomes your arc theta square by 2. Okay, so if you take multiple strips like that and integrate arc theta d theta, then you have arc theta square by 2 as the length of this much. Okay, so the total distance, in that case, y can be represented as pf by 2 plus arc theta square by 2. So the total is arc theta square by 2. Yeah. Now, assuming that, okay. So just take the value of y as such and plug in the value of y in this case to get to this situation where you take out pf plus r theta square and just do d theta of p by 2k plus twice of this theta minus plus of friction coefficient mu multiplied by your radius of roll r normal force p divided by 2k equal to 0. So we have just taken out 2k and divided the whole thing by 2k again, right? So here you have 2k by 2k becomes 1, and here you becomes rp by 2k. Hope you got that. So yeah, this is something we were just discussing just before this part. The friction coefficient is actually positive before the neutral point and becomes negative after the neutral point. So to consider that, we have taken minus plus sign. So you just rearrange this equation, d of t by 2k, you divide that by t by 2k, okay, and then the right side you take out whatever left. Now you integrate both sides, integration of anything differential dy by y is nothing but ln y, so constant c, right? So from that you have this natural log of p by 2k and becomes equal to, this is again the same thing. If you take this as y, okay, then dy becomes this 2 or theta d theta, okay? So you take, suppose you assume Tf plus r theta squared as y, okay? Then Tf is constant, so differential of that becomes 0, right? Plus r is constant, and differential of theta squared is 2 theta, right? Becomes equal to dy, isn't it? So we have just taken that down here to see this also becomes natural log of Tf plus r theta squared. The argument in this case, Tf plus r theta squared minus plus of this term. Okay, so here again you just take out this term called r. Okay, so you then do what is, you do r by tf. You first divide it by tf, so that becomes 1 plus, okay, r by tf of theta square, the bottom part, right? Then you just assume it variable. Then you can see what happens to be the integration of 1 plus an argument y squared. Okay, so that is nothing but tan inverse of y, right? So in this case, our y is nothing but root over of r by tf, right? So when you do that, because this is an argument, this part also comes out here. You can say this root over of r by tf, right? If it is something a, okay, so this a should come out as 1 by a. These are from undergraduate mathematics. So I hope you guys know these things. In that case, the expression comes down to p by 2k if you take out log from all the sides, and then this side, this term becomes exponential. Okay? And we have just replaced this particular term twice of root r by tf, and inverse of root r by tf. Tf is your thickness, okay, initial thickness. Then theta is your angle. So when you replace that, the P, normal force, divided by twice of K, that is the strength coefficient, becomes equal to some constant C into y by r into the power minus plus of friction coefficient into this lambda, okay, whose expression is shown in the third brackets here. Okay. So from that, what you do is just plug in the values of y in case of initial and final case. Okay, so initially, let's suppose it is ti, and finally it becomes tf. Okay, so you just plug in the values of ti and tf. You can find the corresponding pi and tf, right? So that way you can find out the expressions for pi by 2k and tf by 2k, right? And in case of the pre-neutral point region, that is before the neutral point is reached, to take the constant c as c minus, and after the neutral point is reached, to take the constant c as c plus, right? So just a simple rearrangement would give you the values of the C minus and C plus values constants. Okay? And you can just again put back this C minus and C plus values to find the P by 2K before and after the neutral point regions. So these expressions, right? And yeah, sometimes it can happen that uh, there are some losses at the bearings which are supporting the rolls. Okay? If you don't know the rolls, these are rolling, right? So there should be some bearings over which these are rolling to avoid the friction, right? So these bearings can also offer some frictional loss. And to encounter that, we generally just take the frictional loss as friction coefficient mu multiplied by f by 2 into dB, that is the dia of bearing into width, okay? Angular frequency omega. So the thing is that I'm not going to the derivation of this particular expression, but if it somehow comes in exams or something, then you should know that you have to account for the bearing loss also. Okay. Now, at the neutral point, this thing becomes equal. Okay, so this thing becomes equal. The force before and after, or pressure before and after, you just equate them to find out this lambda at the neutral point. So this lambda actually gives the location of your neutral point, right? So you can find lambda through this particular expression, and once you have got that, the role separating force then becomes easy. So this P is your this P be your pressure, then our cos theta d theta. Here we are not considering theta small, and here again we are taking down theta small. So cos theta goes away and becomes 1. When you consider theta small, the cos theta becomes 1, and you come out to the force as PR d theta from 0 to theta I, okay, the initial point. And the total one, you can bifurcate this to T before and T after terms, okay, up to the neutral point and after the neutral point. So that is how the derivation is carried out. I think you have now some answers to your doubts which may have arisen when you are studying this rolling process. Okay? So given that, let's take up a quick look at the drawing process, which is another major forming process which we encounter. So suppose this is a wire which is drawing. So we have two types of drawing. Okay, so one is your wire drawing, this one, and secondly we have a deep drawing, a cup drawing. Okay? So that we would also quickly look at now. Similar to the earlier process of rolling, we just take up a street, okay, just resolve the forces acting on it into its sine and cosine components and do the force balance like that. To and then just you rearrange. Okay. Suppose this comes up to this party, of course, you neglect the higher order terms, right? And the smaller terms in which two differential terms gets multiplied, right? You just ignore these terms and you come up with this particular expression. Okay? So now you just divide that by r times of dr to come up to this expression, and then you just 2 drtx as 10 alpha. From here you can see that this part is a dr and the thickness is a dx, and if this is your angle alpha, so 10 alpha is a dr by dx. You just replace that dr by dx as 10 alpha, so it is dx by dr, so it becomes cot alpha. Okay, and here 10 alpha and cot alpha becomes 1, so in this case it goes away, but here it comes. Now, in the next case, what you do is just replace these things you have done earlier, right? The way we found out your this is called as a flow stress sigma naught. This is stress in a rest direction. This is you can say the stress or force point area. Okay, internal uh, resistive forces is also called as a stress point area, right? So just to replace that uh, sigma naught minus sigma x, okay, and from that will come up to this particular expression. So after that, this is simple derangement, and you have just considered mu cot alpha as a constant b. So this stands for mu cot alpha here, and you then just integrate the both sides to find out this particular expression where you use the boundary conditions such as your back pressure sigma b. Okay, this happens at the initial point Ri, and finally it becomes the drawing stress sigma t. You just plug in the values at Ri. You use sigma b in place of sigma x, and then in place of Rd drawing stress, you use sigma d here. So when you have done all these things, you finally get an expression for drawing stress. So this equation is flow stress sigma naught multiplied by 1 plus b, which is a constant mu cot alpha. And then you have this 1 minus of RF final radii by initial radii of the wire raised to the power twice of b. Plus this thing comes up whenever there is a back tension. Okay? If this is not there, back tension is not there, then this term becomes zero. Sigma will become zero. Okay? And this is the maximum reduction case for sigma b equal to 0, and the ratio of drawing to flow stress is 1. If you are asked in the paper that you have to find out the radii or something in case of maximum reduction case, remember you should use this condition sigma d by sigma naught is 1 and sigma b is 0. Now suppose that your b also becomes 0. B is equal to what? And b is equal to mu cot alpha. Okay? So when there is no friction, then mu cot alpha becomes 0 and b becomes 0. So in that case, this equation comes down to sigma d equal to sigma naught natural log of a naught by a1. This is the initial area and this is the final drawn area. Okay. Now you just take out sigma naught to the left. If a natural log of a naught by a1 is the ratio of sigma d by sigma naught, which is equal to 1 in case of maximum reduction case, right? That just discussed here. And in that case, your a naught by a1, if this is 1, then e to the power 1 and becomes equal to e. So which is nothing but 0.63. So this has been asked multiple times in several papers, exams, such as GATE and all. So you, this is the reduction percentage, okay? At ideal case, maximum reduction case is 63.2%. Now this is another direct formula to find out the reduction in okay, maximum reduction car pass. You can also use that, and this is to find out the degree of drawing operation. This indirectly gives you how much can you go down in the dia with every operation. So that is how we go through the drawing process. So this is actually wire drawing process, right? I hope this is clear. In that case, we have a problem from this wire drawing process. Okay? Here a steel wire is drawn from an initial dia of 12.7 millimeters to a final dia of 10.2 millimeters at a speed of 90 meters per minute. And the cone angle, the half cone angle of the die is 6 degrees, right? The alpha value. And the coefficient of friction at the chopper interface is 0.1. Okay? Now, two types of tensile strengths are given to you. One is that at a tensile test strength. Okay? and the other is at a particular strain of zero point 0.5. So, pardon me, this is actually OF. Then assuming linear stress strain relationship for the material, you have to determine the drawing power and the maximum reduction at the same time, right? Considering that no back tension is applied. So just give it a try and then we'll discuss it quickly. All right, so let's look at the solution for this particular question. So in that question, this half cone angle alpha was given as 6 degrees, okay? And initial and final dia were given as 12.7 and 10.2 mm respectively. The velocity of drawing process was 90 meters per minute, coefficient was 0.1, sigma initial was 207, as found from the tensile test, and at a particular strain of 0.5, it was your 414 Newton per meter square, right? Back tension was 0, as it was given. Okay? Now, you have to find out the drawing stress or drawing load. Okay? So first you find out that this sigma b becomes 0 because no back tension has been applied, and the average flow stress becomes the average of initial plus final by 2. However, the final one you have to calculate because it is not exactly given. This given that for a particular for this particular material, 414 megapascals of strength is achieved at 0.5 of strain. Okay? So you just plug in to this formula, plug in this values to this formula where sigma becomes equal to sigma initial. Okay, plus this is your natural log of A1 by A2 initial final area. And this is actually a strain, and this is your E modulus. Okay? So when you plug in all these values, you find that sigma F becomes to 388 Newton per meter square, right? Then just you find the average from this formula, it becomes sigma naught. It gives you sigma naught is 297.5 megapascals. Okay? And the constant B is your new port alpha. At alpha is 6 and friction coefficient is 0.1. Find the value of B and plug into the value of drawing stress sigma, okay, which is nothing but 211.2 megapascals. So that pretty much answers this question, and that case we proceed to our next one. Sorry, so we were asked to find out the drawing power. Okay? So once you have find out the maximum reduction, so once you have find out the drawing stress, that pretty much simple. You just multiply that stress with the area, okay, and to get the force, and then multiply that with the velocity to get the power, okay? Which comes out almost to 25.887 watts. And then the maximum reduction, we can find that out using this particular formula, which comes out to be 3.1 mm. So this is the maximum reduction case which we have discussed. And you consider plug in the values of all the parameters of B, and that D is your final dia from which you can actually find out the maximum reduction purpose, right? So from that, Di minus Df, which is final, gets you the maximum reduction is 3.1 millimeters. Okay. So now we have come down to the concept of deep drawing. We'll quickly go through that, right? So in case of deep drawing or cup drawing, this happens to be the setup where you can see a cup is being drawn through this particular job. Also, this is the job. This happens to be the blank, okay, which supports this punch, right? And it happens radially, so this is called as a radial drawing. Okay? FH is the force on the blank. It also called as a blank folder force, not if you know. So this is actual longitudinal die drawing, right? Okay, so shear is stress, and our strength coefficient is almost equal to sigma y divided by √3. Sigma r is a radial stress, sigma z is a longitudinal stress. Okay. Now you just do the post balance similarly as the earlier two cases where you do RD sigma r plus sigma r dr. Okay, you just neglect the terms which contains double differentials, and you just go down to this particular equation, so sigma r by 2k equal to constant c minus ln r, natural log of r, the radius, okay, of the particular chunk. Now you know that at r equal to rj, the final sigma r becomes mu fh divided by pi of rj multiplied by the thickness of the particular sheet T. So this is your force. This is the area pi r into T. Okay, you know that for a thin sheet, this time this is the happens to be the cross-sectional area. And the mu is the frictional force. So frictional force times frictional coefficient of the force. So this whole thing becomes your sigma r. Okay, radial stress component, just plug in the value of sigma r here, and you can get the constant C. Plug in back the constant of C in this equation, and you find sigma r by 2k as this particular equation. Now, in that case, you can just plug in the value of r as the drawing radius d, okay? The cup radius d. You can see this one RD value. So once you do that, you can find out the sigma by 2k value, the particular radius RD. Now from that you can find the radial stress, and just looking at the belt pulley formulation where sigma z divided by sigma r gives you your e to the power of exponential of mu pi by 2, or pi by 2 is the subtended angle, right? So we just do that to find the sigma z, okay, equal to sigma r at r equal to drawing radius rd, okay, to multiplied by exponential of mu pi by 2. So from that sigma z, finally you can find the drawing force. So that is pretty much about deep drawing. Hope it is clear to you all. So in that case, we'll gradually shift to the next part. Before that, these are simple empirical relations for the blank dia for a particular D which you want. Okay? So these are for different conditions. You can have a look through them. Multiple choice questions to be asked from this part. So let's move to the next case. So now we take on a different track. So it is actually asking about a casting process, right? So there are two pouring basins in place of one, pouring basin 1 and 2. And you have to find out the case when pouring basin 1 is functional, what is the mole filling time? Pouring basin 2 is functional, what is the mole filling time? When both are working together simultaneously, what is the mole filling time? Okay. So this is what the question is demanding from you, and then the given dimensions, which is 60 cross 60 for the mold cavity, 100 centimeter to the total height, 75 to the height of the mold, and 25 to the height of the pouring basin. Okay. So given that, you just find it out, just try a little, give it some time, and then we'll discuss it. Okay? Or rather, let's discuss it right away, because we are running short of time. It's the last session, and our more topics to cover. So first question was, you have to assume that only basin 1 is functional, okay, and basin 2 is not working. So suppose basin 1 means it is indirectly, this one is basin 1, so it indirectly becomes a top gating system, right? So for top gating system, you just use the Bernoulli principles. You know how to use them for a casting process. You just consider P1 by rho g, the pressure head, the velocity head, and the height head. Okay. For points 1 and particular point 3 at the end of the basin, at the entry point of the gate. So if you take this as the base, then H3 becomes 0, right? H1 remains. Then velocity at V3 has to be found out, and then pressure at 3 becomes 0, because this is exposed to the atmospheric pressure, right? And P3 becomes 0. Okay, then Q1 is also exposed to the atmosphere, so Q1 is also zero, and V1, the velocity of the entry point, uh, is zero again. Initial velocity has been assumed to zero. In that case, your V3 actually becomes root over of twice of the ABT extension between G into H1. Okay, the height difference between the 2 points. You find out V2 is 2.21 meters per second. And then you can find the mole filling time TF as volume divided by choke area, which in this case is this part. Okay, which is same for all the gates though, and then you just multiply that with the V3 value. So the volume of the mold, is been given. Area is cross-sectional area 60 centimeters square, and the height is 75. So get the volume of the mold in that way, and here you have the area, which is just so the area is your 10 into 10 power minus 4. You have been given that all the gates are pretty much having the similar area. And 2.21 is the velocity which we have just found out. So this is 122 seconds for the first gate, okay, which is acting as nothing but a top gating system. The next we have a bottom gating system on. Okay, considering that the top gating system is in ideal condition, the bottom gating system is working. So you also know that how to find this out. Okay, so again, use a Bernoulli equation between 1 and 3, the entry and the points. Okay? And then take another equation between 3 and 4, the final position inside the mold cavity, to just find out V3 as root over square root of 2g ht, its total minus h, which is a height of the mold at any point of time t. Okay, I just take the Bernoulli equation between 3 and 4, 0.3 and 0.4, to find out the pressure at the point 3, okay, which is rho g into the h, which the molten metal is fixed inside the mold cavity at that particular instant of time. Now, using that, you use the continuity equation, right, which is your A1 P1, you know that, okay, between any points A1 P1 equals to A2 V2. This is the continuity equation. You just plug in here at the mold. We take the velocity is dt, rate of change of the height with respect to time, and then at the point V, at the entry point, we take the area of gate into the velocity V3, okay, which we have found out right here. So we just plug in the values and integrate them to find out the solidification time TF, mold filling time TF is twice of AM by H1 by root 2 root over H2 minus root over H2 minus Hn. This is the total height, and Hn is the mold height. Okay, AM and Vg are the mold and gate area respectively. We just plug in the values as given in the question, and we find that it is 81.27 seconds. So lastly, where we arrive is when both of the basins work simultaneously. Okay, this is a case which you need to think upon. So here both are acting simultaneously, right? So when you find out okay, so this is the actual concept which works, right? This is an alternative method which simply you have found out at your aptitude level questions. You can directly solve that using two pipes filling a cavity at the same time. So one has the rate of both are given to you. You have to find out when what would be the rate when both of them works together. Okay, so this is one method, and this is another method. Okay, this is your simple aptitude problem method. You can simply solve it, okay, using your aptitude, and this is what leads to casting. So there should be a constancy between the total entry to this mold filling cavity, this mold cavity, and the volumetric change inside the cavity. Okay? So every top plus the bottom should be equal to the rise in volume of molten metal inside this particular cavity. So just that simple steps. After that, you take out the area of head, feet top plus the bottom, we consider this to be, and feet top we have calculated in our first question, first part of this question, the bottom we have calculated, and then we simply come down to the mold filling time, TF is 40 seconds only, right? I hope it's clear to you all. Now we move to one of the left topics, which is MRI and abrasive jet machining. It's similar to your ultrasonic machining process. Okay, you just have to equate the kinetic energy of fluid or abrasives. Okay, and be equal to the plus 16 energy. Okay. So when you have done that, you just place the kinetic energy as half of mv square. And the strain energy is half of average of F, the force acting on the grid into the HW, okay, the penetration depth, right? So you just replace the value of mass in terms of dia and density of the particular particle, and then you just replace this force in terms of area into the stress, okay? And then HW remains as it is. Now you know that the hardness is always comparable to the strength, as you have seen in case of your ultrasonic machine process. Okay, so just simply you take out the HW, okay, depth of penetration or indentation depth, as square root of density by 6 of HW multiplied by CD. Okay. So in that case, we have used this D, so the dia of the indentation as square root of dia of the grid, the indentation depth multiplied by 2. So the derivation you can check the ultrasonic machining process. I have discussed it earlier. So just to replace it and finally find out the Q, the MRR. Okay? That should be actually dependent upon the volumetric removal per feet per cycle into the number of impacts. Okay. So the volumetric removal is simply considering this the hemisphere, right? Considering this as a hemisphere, the indentation, the volume removed can be considered as 2/3 of pi d by 2 cube. Okay, and the number of impacts then becomes a total mass to rate divided by the mass of each particle. Okay, so that way you can find out the number of impacts, and then you just go through these steps to simplify it, and finally find the Q or MR in case of AGM has this constant 1.04 mass flow rate multiplied by V raised to the power 3 by 2. V is the velocity, rho is the density raised to the 1 by 4, and H is the hardness. Okay. And if you consider that the mass flow rate is proportional again to the cube of d, that is of the grid size, you can actually take down this relation. So that is the frequency. So that is the number of particles moving in fact is the dia, the velocity, density, and hardness. Okay? That's the constant. So that is the way you find out the MRR in case of HM process. Uh, there's nothing much new. It's similar to ultrasonic machining process. You can have a look at it. So having said that, we'll move to a case in which you have to find out the MRR due to freely moving particles which are deflected away from the workpiece. Okay. So we are not actually looking at the gross or bulk material removal. We are rather looking at the material removal by the particles which are reflected away from the workpiece, okay, after impacting. So this is for the general MRR transition model upon particle impingement, which we have seen earlier. And this is how the reflected particles, when they fall back from the workpiece, the amount of material removal they do, right? So if you take the y, the path being varying as sinusoidally as a sine of 2 pi mu t, mu with the frequency, then your velocity becomes 2 pi mu into a in the amplitude. Okay? Now the kinetic energy, just as we have discussed in this abrasive jet machining, becomes half mass into velocity squared. You just replace all the terms to get the maximum kinetic energy. So this expression, and then you consider the force which increases linearly with indentation. Okay, then in that case, your kinetic energy maximum becomes half of Fi max dash into h dash. Okay, dash to help you understand that this is due to the secondary particles, okay, which are reflected away from the workpiece. So in that case, you just rearrange the values, okay, to get the Fi max as pi d of hw dash of hardness capital HW. Okay. So using that value in this particular expression for maximum kinetic energy, we finally find out the indentation depth as pi times of root over twice of density by twice of hardness multiplied by dia of the particles with its frequency and the amplitude. Okay, so this is the depth of indentation for a freely moving particle in the case of reversing. Okay. And this is one more concept that actually the particles are not completely spherical, and the outer periphery is very irregular, having multiple small spheres. You can assume them to be whose each one of have a dia of dy, right? So when you replace that directly, you have seen that the variation of dia is as 1/4 power. Okay, so practically that varies as simple d. Okay? This happens when you replace d as d1. Okay? So this is one thing, and then this is something actually we had discussed some time back, where you have to determine the tool shape in 3D. So the process follows same, so I'm not going to the details of this derivation. Of course, the presentations will be made available to you. You can look at the steps similar to the 3D case. Just one more angle. Okay? So you can look at it back at your home, and this slides will be made available to you. So after that, finally, we move to the last topic, where we discuss some of the concepts from additive manufacturing, or you can also relate it to your casting and any types of metallic solidification process. Okay? So there is a fundamental difference between solidification of a pure metal and an alloy. The thing is, alloy solidization takes place over a range of temperature, whereas in case of pure metal, it happens at a constant temperature, Pf. Okay? So that is well known beforehand, but in that case, depending upon the cooling rate, the behavior can be pretty much different in case of different kinds of alloys, or the same alloy can behave differently depending upon the cooling rates. Solidification can happens here at a wider range of temperature, right? So that creates the problem, that creates the main difference in respect to pure metals. So if you look at it, so pure metal solidifies at a constant temperature, which is equals to its freezing point. It's the same as the melting point. However, in case of alloys, we find a range of temperature rather than a single temperature for the alloy to freeze. Okay? The cooling action causes grain seam, causes the grains in the skin define. So the grains which are the skin happens to be very fine and randomly oriented in case of your uh, pure metal solidification, whereas in the other case, you can find a variety of grains depending upon the cooling rates and multiple other factors. Okay? So you can have columnar grains, you can have globular grains, you can have dendritic grains. Okay? So all these things happen because the freezing is happening over a wider range of temperature, right? So actually, what happens is after the skin formation, similar to that of pure metals, what happens is small dendrites begins to form away from the walls. Okay? So these dendrites structures protruding away from the walls of the uh, particular tube or pipe, and then what happens is these dendrites in turn restricts the liquid flow. Okay, some of the liquid, some fraction of the liquid just gets trapped into these dendrites. Okay? And in most case, there can happen particle segregation. Particles may get segregated into the liquid, so that can finally lead to density variation in the final product. So this is the main thing with alloy solidification. You can see this segregation thing, right? So yeah, so that mainly is the way through which you can find the differences between pure metals and alloy solidification difference. So next, we move to droplet formation technologies, right? So this is something related to your the way in which you deposit metals layer by layer, the metallic powders, or even you can say polymer powders, whatever you can say in case of additive manufacturing process. Right? So actually, that is a particular matter of concern sometimes, how the droplets are being deposited. So actually, there are two modes of expulsion. One is continuous mode CS, and the other is drop on demand mode DOD. So we'll quickly look at the these two particular kind of droplet formation technologies. So It is mainly depend. It is mainly the main difference is on the way through which the droplets are being expelled. Expulsed. Okay, if that happens in a continuous column of liquid or a discrete or a form of discrete droplets. Okay? So looking at that, you can see that this is a continuous mode of droplet formation. Okay, so where you can see a steady pressure is applied to the fluid reservoir, causing a pressurized column of fluid to be ejected from the nozzle. Because the pressure remains steady, so the fluid ejected from the nozzle becomes continuous. So after departing the nozzle, the stream breaks into droplets due to Rayleigh instability. Okay, so I'm not going to graph the Rayleigh instability. They can say that, of course, the droplet becomes unstable after a particular time, point of time. It has come out of the nozzle and it breaks in the stream. The breakup can be made more consistent by vibrating, perturbing, or modulating the jet at a fixed frequency close to the spontaneous droplet formation rate. Okay? In which case, the droplet formation process is synchronized with the force vibration, and the ink droplets of uniform mass can be formed. Right. So, deposition must be controlled after the jet separate from the jet, because the droplets are being produced at constant intervals. So this is how continuous mode droplet deposition happens. So you can find a high throughput rate as an advantage of continuous mode of droplet deposition. Okay. So these are being applied in case of food and pharmaceutical labeling. And this is one more case in which you do drop on demand. Okay. So individual droplets are produced directly from the nozzle. So in that case, the pressure pulses in the nozzle cause the fluid to be expelled. So you don't maintain a steady pressure, rather we give pulses of pressure. Okay. So that way the droplets are formed only when you desire. So that is why it is called a drop on demand mode, right? So this excitation or pulse formation can happen thermally, electrostatically, piezoelectrically, acoustically, many other processes can be there. So piezoelectric actuators and thermal ones are the most widely used currently, right? Now, from that, we come to one type of additive manufacturing called as printing process. Okay, so you know that inkjet printing is also a kind of additive manufacturing process. Probably these are now being used in flexible electronics and fabrication of flexible electronic items such as the wristwatches or smartwatches which you wear, ranging to some highly miniaturized batteries, sensors, which can actually glue to your skin and take the shape of your skin. So there the structures are actually being printed. This is actually another type of additive manufacturing process. So in that case, the fluid, the energy imparted by the actuation method to the liquid must be sufficient to balance three requirements: fluid flow losses, surface energy losses, and kinetic energy. Okay. So that way, the energy which is supplied should actually account for all these losses. Now, these are the explanations of this particular requirements. Okay? Like the surface energy requirement is additional energy needed to form the free surface of the droplet, and kinetic energy is required to propel the liquid from the nozzle towards the surface or the substrate. Okay, and then this is the fluid flow losses, which originate from conversion of kinetic energy to thermal energy. Okay. These things should be taken care of as the total amount of energy which is supplied to the droplet, right? So before the fluid leaves the nozzle, the positive effect of the driving pressure gradient accelerates it. Okay? whatever driving pressure you are supplying, it accelerates it, but the energy loss happens because of the viscous flow and the friction, generated friction. Now, the kinetic energy with which it leaves the nozzle, the ink leaves the nozzle, must be enough to cover the kinetic energy of the fluid up to the substrate, right? As well as the surface energy, which we have just discussed now, right? And the flow is, so these are repeated things, and then this something relates to how the flow is described. Okay, so in fluid mechanics, you must have been acquainted to Navier-Stokes equation and continuity equations. The solution finally is the Hagen-Poiseuille law, in which you find that the total pressure which is given uh, depends upon all these particular factors. Okay, but Q is the flow rate, R is the fluid radius, okay? And then sigma is your surface tension, okay? And then this expression is actually applicable when the nozzle is a long glass tube, and also when the fluid happens to be viscous. So this is an illustration of how the pressure varies with viscosity on different dia of a particular pipe, a tube through which the fluid flows nozzle, right? You can see as the nozzle dia reduces, the pressure increases, right? So linearly the viscosity. Yeah, that pretty much completes today's lecture, and hopefully this is where we conclude the problem solving sessions which have been introduced by NPTEL recently. I hope you guys have been benefited to some extent to the sessions, and yeah, so all the best for your exam, and if you have any doubts, and please go on. We still have around 5 to 10 minutes left.
Hello, sir. Hello,
Yeah, please go on.
sir. You whatever you taught in the problem solving session is this are not included in the real session. So I think
Sorry?
whatever you have taught in the problem solving session, the theory
Yeah,
part,
yeah.
this part is mostly I found that mostly I think 50% of these parts are not included in the real video part. So
Yeah. So actually, these sessions are were actually aimed to clear your doubts and solve.
I also thought that, but I just came here and that found that you are supplying new theories or new something new papers like that in front of you.
So what things, whatever things you found new, may actually help you out. So we have covered whatever have been taught in the last session only. So today's session, I just wanted to look back at some of the things which are not covered earlier. And actually
This is
from,
something related to the fluid mechanics and something like that.
no, this is actually, so you are in which year now in your BTech? You are a BTech or
Yes,
postgraduate?
I'm a BTech third year, sir.
Okay, so yeah, so these are actually related to your additive manufacturing thing. So a basic fundamental of that was covered in your actual course by Shantanu sir, and these are some additional things. So you may not find that relevant to this course requirements over NPTEL, but these may help you out ahead if you go for higher studies or some research things. So this is actually related to solidification. Some of the topics are related to solidification process. Some are related to your flow through the nozzles, which you need to actually optimize for this kind of printing, jet printing, which is a kind of additive manufacturing actually. So these days, you rarely find core manufacturing happening out at the premier institutes. Uh, we work on interdisciplinary projects where actually you may come across all the disciplines of mechanical, maybe fluid, thermal, or whatever. This additive manufacturing thing is completely a cross of all the specializations, all the disciplines, all the subjects you find, starting from thermal, manufacturing, material science, fluid, whatever you can think of. And even these days with automation and things, electronics, as well as artificial intelligence are getting included. So yeah, I hope you get the point.
Sir, I got the point, but I still miss very much the part of this lecture. I have actually I have no idea about there is in the problem solving there is any new things to be taught. So I think I
Mhm.
have to cover up in few days. I don't know.
So these are available over YouTube, and the slides are also available there. So exactly, I
Yes, sir.
didn't. Hmm.
Yes, sir.
So once the topics, regular topics which are taught in your class had been covered, and then I wanted to take it ahead to some additional topics and contents, which may add to the knowledge depth you have. So
Yeah,
that's it.
yes,
And
yes, I got the point. Okay.
uh, yeah. So you can find them. The videos are there in YouTube, and also the slides are also being shared into you. That's not an issue.
Okay, okay. Thank you, sir.
Yeah.
So these type of things are also included in the exam. These details things.
No, no, no. This much detailed things will not be included, but you may find the basic understanding of different types of additive manufacturing processes. Last session, we had discussed those SLM, SLS, DED processes. Okay, what is the basic principle through which they work? What is the advantages and limitations of these processes? Today we have discussed inkjet printing. So these are actually the major additive manufacturing processes which are now being worked on. So we might not go into these formulations and derivations from these topics, but the basic concepts and understanding may be examined itself.
Okay. Thank you, sir.
Yeah. Okay.
Good night, sir.
Yeah.